Hello everyone. Welcome to session 7 and the last session of this MOVIDRIVE B intermediate training series. In this session, we are going to discuss 10 common faults that can occur. We will mention some helpful tips and software tools that you can use to try and determine the root cause if you encounter any of the faults that we will mention here. When having to diagnose an application, there are a lot of avenues that you can take. It's best to go through a process of elimination to narrow down the cause by working through the chain of devices and focusing on devices that are interconnected before going to other devices that are just neighboring to the potential problem devices. I recommend to start diagnosing the easiest items first. These could be things like checking the fault history, taking measurements with a multimeter, looking for bad electrical connections, etc. If you start diagnostics with time-consuming tasks like removing and replacing components, you may be wasting efforts on items that aren't the root cause. It's also possible to cause damage to new components by installing them into a problem situation before knowing the root cause. Also, it's good practice to recheck items again or have someone go behind you to check as well, since it's easy to make a mistake or overlook something in your diagnostic process. If your motor is controlled by a MOVIDRIVE, one of the best diagnostic tools you have is the MOVITools software. If the problem situation is coming from a device that is in the same control chain of the MOVIDRIVE, then I would recommend to use the Scope tool to get a recording into the operating conditions of the inverter to narrow down if the cause is upstream of the MOVIDRIVE, such as the PLC, contactors, or supply voltages, downstream of the MOVIDRIVE, such as the motor, encoder, or load of the application, or internal to the MOVIDRIVE, such as the parameters, the IPOS program, or hardware. If you need a refresher on how to use the Scope tool, you can go back and watch the videos for Lab 7 and 8 to learn how to use that software tool. However, we will do a brief overview of the settings in this video shortly. With any troubleshooting you do, you should be qualified and have a clear understanding of how the devices are interconnected and how each component operates. This is because there are moving mechanical pieces and electrical hazards that you must be aware of so that you can lock the machine out mechanically and electrically to safely conduct your troubleshooting. When you first detect that the application is not operating properly or that it's generating a fault, you'll need to gather information about the states of the components when the abnormal behavior occurs. The first place you can gather information is from the 7-segment display on the MOVIDRIVE. It's a quick viewpoint to determine what state the inverter is in at a given time in its operation. There are some codes that indicate normal operation and others that can mean problematic conditions. We've discussed some of these in the previous lab exercises, such as codes 5, H, and A, but all of the codes above represent normal operating states. Also, some of these you would only see if the MOVIDRIVE was configured to operate in that mode, such as standstill current, torque control, hole control, and others. It will be helpful to learn what codes you see on your MOVIDRIVE, since it's easier to identify what operating modes the equipment uses. There are some codes that are inverter statuses of the hardware and are not operating modes. It's common to see a solid number 8 when powering up the MOVIDRIVE, or you may see the lowercase letter t when the field bus is waiting for process data to start from the upper level PLC. If you do see a solid number 8 or the letter T status being persistent for a considerable amount of time, then there is likely an issue that you would need to troubleshoot. We've previously shown the blinking dot in the bottom corner of the display, which indicates that the IPOS program is in run mode and not stopped. If you know your MOVIDRIVE is using an application module or a custom IPOS program and you don't see the blinking decimal, then the program is in stop mode and needs to be restarted, or the program has been deleted. In either case, you will need to connect with the software to determine what happened to the program. There are also codes that indicate a stopped state for the MOVIDRIVE. I will mention that a stopped state doesn't mean that it's safe to enter the equipment to diagnose it. It just means the motor isn't being commanded from the MOVIDRIVE to rotate. Some of these are normal and some are not. If you need a refresher on the voltage and digital input and output locations of the MOVIDRIVE and the purpose of each plug, then you can go back and watch the video for session 2 to learn about those. You should know the purpose of the connections since some are 24 volts and other ones have an excess of 700 volts. Never disconnect any of the connections while the MOVIDRIVE is powered because it can cause an electrical arc. If you see a number 0 on the display, that means there is no high voltage supply and the MOVIDRIVE is only being powered by an external 24 volt supply. If you measure with a multimeter and determine that the high voltage supply is present with this on the 7-segment display, then there could be an issue with the MOVIDRIVE hardware and you would need to replace it or send it to your local SCW office for evaluation and possible repair. The letter U status is displayed when the safe torque off connection on the MOVIDRIVE doesn't have 24 volts. This is normal if a safety circuit has been tripped because those are typically wired into this X17 port. If a fault does occur, it will always be flashing and the fault code will display after the letter F. In this example here, you can see the F008 code being shown, which is a speed monitoring fault that we'll discuss in more detail shortly. You can go to these pages here in the MOVIDRIVE system manual to read better descriptions of the fault codes. Lastly, if you see a solid letter F that is reversed, this is not a normal fault condition, and this only happens when the hardware of the MOVIDRIVE is no longer communicating with the memory or processor. If you see this, there isn't much you can do in the field to resolve it. The MOVIDRIVE should be sent in for evaluation and repair, or it should be replaced. Before you connect with the software, if you have a keypad, you can use it to quickly inspect the fault history to get a better look at the operating conditions of the MOVIDRIVE when the fault was recorded. We demonstrated how to use the keypad back in the video for Lab 10, so you can go back and watch that to get a refresher on how to access the fault memory and other parameters. In the previous labs we've gone through, we focused heavily on using the software, and the Motion Studio software offers the most features to commission and diagnose applications over using the keypad by itself. We introduced the fault memory back in the video for Lab 2, but I will briefly go over what information you can find here. The fault memory is found in the 08 parameter folder, and it stores the last 5 faults on the MOVIDRIVE. Memory 0 is the most recent, and memory 4 is the least recent. When you click into the memory, the top of the window will list the fault code, the sub-error code, if there is one, and a short text description of the fault. If the MOVIDRIVE does issue a fault, the memory will have a snapshot of the state of the inputs and other conditions at the moment the fault occurred. In the binary inputs and outputs checkboxes, if the box is checked, that means the input or output was on, and if it's not checked, it means it was off. We'll cover the 10 most common faults next, but in the fault memory, some commonly helpful information is the motor speed, active current, and output current values. Those values will help you determine if the motor was traveling when the fault occurred and if there were abnormal speed or current values. You can also use the operating and enable hours to determine how far apart the faults occurred and compare it to the present hours in the 01 status displays parameter. Next, we'll discuss the 10 most common faults that we get questions about into our engineering departments or travel to customer sites to help troubleshoot. These faults we will go over are not in a specific order, but are grouped together based on potential causes, because sometimes the same root cause can produce different fault codes in the MOVIDRIVE. The first fault is an F01 overcurrent. The description can make it seem like it's related to motor overcurrent, but this fault is not related to motor overcurrent, but rather overcurrent at the output circuit of the MOVIDRIVE. If the MOVIDRIVE issues an F01, it's the internal circuit shutting down to try and prevent permanent device failure. If you're commissioning a new MOVIDRIVE and you get an F01 when you try to operate it, then there is possibly an issue with the motor parameters, the ramp times being short, or the MOVIDRIVE is too undersized compared to the power requirement of the motor. If you get an F01 with an existing application and there hasn't been a change to any parameters or speed and ramp set points, then there is potentially an issue with a component in the device chain. This could be with the power cables, brake resistors, filters, or internally the MOVIDRIVE itself. The next fault is an F03, which is a ground fault. This is a very specific fault, and it's when the MOVIDRIVE circuit detects voltage flowing on the ground connection. If you're getting an F03, it usually is caused by a damaged component in the device chain, loose electrical connections, or during troubleshooting, wires have been swapped to the wrong terminals, such as landing a power wire on the ground and vice versa. I will mention that for each of these 10 faults, I'll be listing items you can check if that fault occurs. These are not exhaustive lists, but are just common items that have been causes for these faults to happen. Applications vary in power, accessibility, and complexity. Some items may be difficult or unsafe to check. You will always need to work safely and within your expertise for the application. If you are unfamiliar with the device operation or checking it creates safety risks, then do not attempt to diagnose it and find other methods to diagnose the application and individual components. We discussed this back in the video for session 4, but you should inspect your motor nameplate before you start diagnostics of any components on the motor. If your motor nameplate has a box with the letters FS and a number inside of it, that means the motor was assembled to a functional safety standard. These types of motors are very common. Here is a list of the different functional safety combinations you can see on a nameplate. And if you have any of these combinations that use a functional safety brake, encoder, or both, you will not be able to remove and replace any of those components for troubleshooting. If you think the brake or encoder is defective, you would need to replace the entire unit. These components can only be replaced by someone that has a functional safety certification, and there is a documented process that has to be followed when these units are worked on. So if you see this on your nameplate or any mounting screws on the motor are covered with yellow paint, you will need to stop and contact your local SCW office for assistance. If you are troubleshooting an F01 or F03, some of the same conditions can cause either fault. Specifically with the F01, if it is a new application and you're commissioning it, then check the parameters and that the correct size motor and inverter combination was installed. If you've ruled out the parameters or component sizes as the cause, then for the F01 and F03 faults, you could start doing more in-depth troubleshooting of the application. If there is the ability to isolate the inverter from the other devices, It will be helpful to narrow down if the error is coming from within the inverter or external to the inverter. When disconnecting power cables, you should check for the absence of voltage and make sure the machine is mechanically locked from moving, because it's possible for the application to fall or release stored energy if it's not able to create motor torque because the power cables are disconnected. The F01 and F03 are specifically with the output side of the inverter, so you will want to check downstream devices like motors, filters, chokes, brake resistors, and power cables. Since these faults deal with electrical issues, be extremely careful since cabling may be damaged, loose, or landed on the wrong terminals. The next fault is probably the most common because it can be a catch-all fault with numerous root causes, ranging from something simple to complex problems. This is the Fault 08 speed monitoring. The description of the fault may not seem like it has a relation to the motor current, but unlike the F01 overcurrent, this fault does commonly indicate that the motor is pulling excessive current from being overloaded, but it could also be with many other causes as well. These causes can range from issues with the motor commissioning parameters, such as the motor voltage, frequency, ramp time, the speed, or performance tuning. It could also be caused by components like the mechanical brake on the motor, the brake rectifier, or reversed motor or encoder leads. The next fault is an F42 lag error, and it can also be caused by the same things that an F08 fault can be caused by, but it's specific to positioning applications. This fault is generated when the motor cannot maintain the positioning profile to the target position. The F42 can be caused by parameter settings, the positioning scaling in an application module, motor or encoder wiring, and brake issues. If you are getting an F08 or F42 and it's a new application, then you should first check the parameters. The parameters that could cause the fault will vary by how the MOVIDRIVE is configured, but parameters relating to the motor commissioning, the set points from the inputs or the PLC, and the current limits should be evaluated. Here is a list of some parameters that you can check, but this is only an introductory list. There are many others, especially in the motor performance tuning parameters, that could be the cause. If you get these faults and it's an existing application, you should never increase the current, torque, or lag error limits to try and get past a fault. You should first determine why it's happening, because if previous parameters worked for the application, you shouldn't need to change them unless there has been a change to the application. It's possible to cause further damage to the motor or application if you try and bypass these faults or change parameters that you don't understand their function. When you do modify the parameters, you need to keep a record of what you change, because some changes could make the problem worse. You will want to undo the changes if the adjustments make the situation worse. I recommend to take a parameter backup right before you make any changes so you can revert back to it later if you need to. After the parameters, the next thing to check would be mechanical and electrical components. Oftentimes, the F08 and F42 is caused by something mechanical in the application, causing the motor to bind and draw excessive current. These can be the brake on the motor, the brake rectifier, reversed motor phases, or bearings and gears on the machinery. If you have a positioning application, you can use the Scope tool and measure the lag error IPOS variable H495. If the lag error continually increases in the recording, that is indicative of a mechanical bind or the positioning scaling being incorrect. Lastly, it is possible for encoder wiring, like the channel arrangement or electrical noise from nearby power cables, to cause the F08 or F42. You should check those items or replace the encoder if you find that it is defective. Back in the video for session 5, we discussed how to diagnose the encoder, brake coil, and motor phases. So you will need to go back to that session to learn how to check those components. If you do find that the brake coil on the motor is damaged, you must also replace the brake rectifier, since those need to be replaced together. If you don't replace the rectifier, it may cause damage to the new replacement brake. The next fault is an F14. This fault is specific to the MOVIDRIVE and the encoder signal. This usually indicates that the MOVIDRIVE parameters are set up to expect an encoder signal, but it's not detecting any encoder pulses or the data over the communication channels. This often happens when the encoder cable is disconnected when troubleshooting motor or application issues. As soon as you reconnect the encoder cable and power up the MOVIDRIVE, the fault should be cleared. As a reminder, always switch off power before unplugging the encoder cable. It is very possible to damage the encoder card in the MOVIDRIVE if you don't switch off power. A damaged card can lead to a persistent F14 error. If you're getting this error and it's intermittent, then there could be issues with electrical noise from high voltage cables, a worn encoder cable, which is common for cables that travel with the application, or the encoder signal fluctuates, which can be caused by power supplies dropping during travel, slipping mechanical connections, or damaged areas such as a barcode tape for encoder barcode scanners. If the F14 error is persistent and doesn't reset, then inspect the encoder cable for damage and check for loose connections. If you can manually rotate the motor, you will want to determine if the encoder position parameter changes its value as the motor moves. Also, check the motor startup and make sure it matches the encoder that is installed on the motor. If the encoder parameter was changed or a different model encoder was installed without updating the startup, it could cause this error. As a last resort, you can remove the encoder from the motor and spin the shaft to determine if you are getting any pulses in the MOVIDRIVE. You should see the position change by 4,096 increments for every rotation of the shaft, either in a positive or negative direction. If you aren't seeing the correct number of pulses, then you can replace the encoder or the encoder card of the MOVIDRIVE. If you do have to remove the encoder for troubleshooting, you will need to reference the motor after you've reinstalled it. However, if you have a servo motor with a resolver, you should never remove it for troubleshooting, since it has a specific angle alignment that is done during assembly. If you have a servo that the encoder or resolver has been removed for troubleshooting, you will need to contact your local SCW office for support to get the encoder or resolver realigned to the motor shaft angle. The next fault is an F28, which is specific to MOVIDRIVEs that use a field bus for control. This fault occurs when the upper level device, like a PLC, is no longer communicating to the field bus card in the MOVIDRIVE. Potential causes for this are disconnected cables or the upper level device's program has been stopped. If the F28 fault is sporadic, it could be caused by heavy network traffic. Depending on your parameter settings, the F28 fault can reset itself automatically once communication is reestablished. If the F28 fault is persistent, then you can check the network cabling for disconnection or restart the PLC program. Also, power cycling the MOVIDRIVE will force the field bus card to reinitialize, which sometimes can clear from the F28 fault as well. If those steps don't work, then you will want to check the address parameters in the field bus card and at the upper level device. You will want to make sure those don't have any conflicts with any other devices in the network. If the F28 fault is sporadic, then you may want to increase the timeout delay time. If that doesn't work, then there may be more complex issues with the field bus, such as total traffic load, network cable shielding, or interference from other equipment. The next fault is an F31. This fault relates to a thermal sensor inside of the motor winding. If you're getting this fault, it usually means that the motor is overheated and needs to cool before further operation is allowed. This is to reduce potential failure of the motor insulation and windings. This error can also be caused by something faulty, like a disconnected or loose sensor wire, a damaged sensor in the motor, or the motor installed doesn't have a sensor, but the MOVIDRIVE parameters are configured to expect one. The motor temperature can be affected by excessive ambient temperature, debris covering the motor, or mechanical overloading causing the motor to work harder than designed. Also, do not permanently remove the fan guard on the motor. The fan guard is necessary to direct airflow across the motor to cool it, and removing it can cause the motor to overheat. If you're getting this error but the motor is not hot, then you will want to check the sensor connection and make sure it's not disconnected or landed on the wrong terminals of the MOVIDRIVE. These sensors can also be checked with a multimeter. A TF or PK sensor will provide a resistance value for a temperature range, and the TH operates like an open or closed switch. It will be open if the motor is overheated, and it will be closed if the motor temperature is below the trip threshold. If you don't have a temperature sensor in the motor, then you can use a jumper wire on the MOVIDRIVE terminals, or you can disable the parameter to switch this feature off. However, do not do this to bypass an overheated motor. The next fault can also be temperature related, and this is an F44 unit utilization. This fault is specific to the temperature and workload of the MOVIDRIVE and not the temperature of the motor. Things that can cause the MOVIDRIVE circuit temperature to be excessive are high ambient temperatures, such as an unconditioned electrical cabinet with a lot of other electrical devices producing heat, the motor's PWM frequency being too high, causing the MOVIDRIVE circuit to overwork. In some cases, if the motor load continually utilizes 125% or more current from the total capacity of the MOVIDRIVE, it may not cause the F08 fault, but instead it can cause this F44 fault. If the internal cooling fan of the MOVIDRIVE is faulty, it can cause this error as well. If the F44 fault is persistent, then you can check the ambient temperature around the MOVIDRIVE or the operation of the internal cooling fan. An easy way to determine if the cooling fan on the MOVIDRIVE is operating is to lay a piece of tissue paper on top of the control head. It should be blowing if the fan is switched on. Now, the fan isn't always switched on, so don't immediately think there is a problem with the fan if it's not blowing air. The fan is controlled by the heatsink temperature of the MOVIDRIVE. The fan cuts on when the temperature rises above 49 degrees C, and then it will shut off when the heatsink cools below 39 degrees C. If the heatsink temperature climbs to 90 C, then the MOVIDRIVE will issue a fault. You can check the fault memory and look to see if the heatsink temperature was around 90 C or if the utilization was around 125%. If the fault memory doesn't reveal that the heatsink or the utilization parameters were too high, then it could be caused by a high PWM frequency. You can reduce the motor's PWM frequency in the 860 level parameters for the operating mode and the parameter set that the MOVIDRIVE is using when the fault occurs. The last faults we'll mention are specifically with absolute encoders. These are F93 and F95. These faults generally indicate that there is a communication or configuration issue with the encoder. It's possible to get an F14 or these errors depending on the root cause. This fault can be caused by a damaged cable, fluctuating power supplies, a damaged encoder, electrical noise, or the application moving too quick, which can lead to erratic encoder signals. If this is an existing application and you get this fault, then you can start troubleshooting the electrical connections of the absolute encoder. Make sure the cable hasn't been damaged, wires are landed on the correct location, or check for loose wires or plug connectors. Many absolute encoders require an external power supply because of how much current they can draw. So make sure the power supply isn't overloaded or switching off sporadically. If this is a new application, sometimes these faults can come from the position scaling or the encoder commissioning. Some absolute encoders, like lasers, have their own displays for the on-device settings, so make sure those settings match with the parameter configuration in the MOVIDRIVE. You can set up a scope recording for the H variable 509 to record the position of the absolute encoder and look for any inconsistencies. These faults can be caused if there is electrical noise or interference, like something blocking the encoder from reading the position. For example, laser encoders use a reflector to measure the position. If the laser moves off of the reflector or is blocked, these faults can occur in those situations. If the encoder shaft is loose or if it travels with the application, check to make sure it's not slipping. This fault can occur by a slipping encoder because the encoder increment changes are erratic. The encoder card usually isn't the cause for these faults, but you can replace it as a troubleshooting step to determine if it is the cause for the fault. Finally, you can also replace the encoder to determine if the problem still exists with a new encoder. Many times, faults won't be persistent and will be sporadic and seem to occur randomly. In those cases, it can be challenging to troubleshoot because you can't recreate the fault at will to go through diagnostics. If you have a sporadic fault, the best tool available to use is the Scope tool. The recording may not show exactly the cause of the fault, but it can give you clues to know where else to focus your diagnostics. To do that, you will want to familiarize yourself with the measurement values and how to interpret them. In the Scope tool, you'll need to adjust the timing window and how it's triggered so that you can capture the data that you need automatically. If the scope is set up wrong, the recording won't show any useful data, and you'll need to reconfigure it and wait for the fault to happen again. We discussed the Scope tool back in the videos for Lab 7 and 8, so you can get a more detailed instruction and see a demonstration of this tool in those videos, but I will summarize the recorder settings here. At the top of the screen are the measurement values, and this is where you will set the different parameters that should be captured in the recording. The ones I recommend to always start measurements with are the actual motor speed, the set point speed from the inputs or the PLC, the active current, which relates to the torque of the motor in a percentage unit, and the output current, which is the total current of the MOVIDRIVE in a percentage unit. Those first four parameters can reveal a lot about the operation of the application. After those, you have more space to add other parameters, and this will depend on what information will be helpful to your situation. When dealing with encoders, custom IPOS programs, or application modules, it will be necessary to record different H variables to get a detailed look at those. When you select the IPOS variable parameter, it will then show a pop-up where you will need to enter the 4-digit variable number that you want to record. There are many different ones, so you'll need to look into your IPOS variable list for the specific program you're using to find the one that you want to record. In this example, we were setting up to record the motor encoder position, so we typed in 0511 to record H511. When you do record an IPOS variable, it will take up two measurement values. So if you need to remove other values to fit all of the IPOS variables that you want to measure, then it's okay to do that. But I would, at minimum, at least keep the actual speed of the motor and output current of the MOVIDRIVE so that you can determine what the state of the motor was when the scope was captured. The next settings are the pre-trigger and the sample time. With these, you will need to try different combinations to get the best capture for what you're wanting to record. If the scope is set to trigger on a fault, then using a large pre-trigger percentage will have most of the recording before the fault and only a little afterwards. For example, this is where you would set the pre-trigger percentage to 90%, and then the remaining 10% will be after the fault. If you use a small pre-trigger percentage, like in this example, most of the recording is after the trigger event and only a little before. This is useful if your trigger mode is set to start the recording right when the motor starts, like the DB00 brake release signal shown in this example. The sample time is how often the scope will capture the data points of each measurement value. A short sample time gives you a very precise recording, but a very short total time span of only a few seconds. A longer sample time reduces the precision, but it allows you to have a recording that spans 30, 40, or more seconds. In this example, a sample time of 5 milliseconds will result in a total time span of 10 seconds. The next thing is choosing a trigger to start or stop the scope recording automatically. You can set multiple sources, just one or none, and it will only trigger if you manually press the trigger button. In the trigger mode area, you can click the source to tie or untie it to the trigger. If you tie the error source, you'll have an option to type in a specific fault number. If you leave it to the default of 000, then it will trigger the recording on any fault. In this example here, we set it to automatically trigger the recording for an F08 fault or an analog source. The recording would trigger on whichever source event happens first. If we don't want any faults to trigger the recording, then we would need to click the error source again to untie it from the trigger mode. If you choose to use the analog or digital source to trigger the recording, the drop-down menu gives you the same parameter choices as the measurement values at the top. With the analog trigger, you can use a parameter like the actual motor speed or an output current level and trigger the recording when the value meets the conditions that you set. You can click the operator to switch between different cases with the value that you enter. With the digital trigger, you can select something like the process data or an IPOS variable and select one of the bits from a 32-bit range and trigger based on the condition you set. Similar to the analog trigger, you can click the bit state box to select between the different options. You can't set the analog and digital triggers at the same time, so you will need to choose one or the other when you set up your recording if you want to use the analog or digital trigger. The last item you can set is the trigger terminal. This is permanently connected to the trigger mode, and if you don't want to use it, then you can set it to manual. But if you do want to use it, you can choose a digital input or output. It's common to trigger on the DB00 signal, which is the brake release output signal, and you can set if you want the trigger to happen on the signal rising or the signal falling. Once you've got all the settings the way you want them, you have to press the Start button at the top of the screen to send the settings to the MOVIDRIVE, because the scope actually occurs on the MOVIDRIVE and not on the computer. Remember, you can go back to the videos for Lab 7 and 8 to see a demonstration of using the Scope tool and interpreting the results. After you set up the scope recording, there is also a tool called the DataLogger. This tool works alongside of the scope, and it's not required, but it is uniquely helpful in situations where the fault may only occur once in a while, and it's not practical to wait by the application until the fault occurs again. Since the scope runs on the MOVIDRIVE and not on the computer, you have to upload any captured recording before the fault is reset, because it is stored in volatile memory, and after the fault reset, the recording is deleted. With a data logger, if you leave a computer connected to the MOVIDRIVE with this tool running on the screen, it will automatically upload and store the scope files after the trigger event happens. It will then restart the scope to capture future faults. I will caution, for this tool to work, that the computer has to be powered and it can't go to sleep. And if the machine faults, the operator has to wait around 30 seconds before resetting the fault to give time for the computer to upload the file from the MOVIDRIVE. If the fault is reset immediately, the scope recording would be deleted during the reset. To use this tool, you do need to set up the scope first. So after you have set up the scope, then you would come into this tool. And once you click into the data logger, you'll see this settings screen. This software is particular with how it is set up, so you will want to pay attention as I describe the purpose of the settings here, so you don't set it up incorrectly. The top part of the screen is optional, and it's where you can type in application details and comments that can be read later in the file properties after you open the scope file. This could be helpful for you to make notes of the application and what problem you are trying to diagnose. On the left side of the screen, you should check this box if you want more than one scope recording to be stored to the computer, and for it to restart the recording after the current scope file has been uploaded. If you combine the top checkbox with this Wait for Error Acknowledgement checkbox, it will wait for the fault to be reset, and once it's cleared, it will then send the command to restart the scope. I would recommend to keep these combinations of checkboxes selected. If you don't check this box, then the same file will keep being uploaded until the fault is reset. This can clutter your files or use up the total number of log files that you have set. This next checkbox will upload a scope as soon as the total sample time has been reached. This can produce a lot of files and even upload recordings when the application is at standstill. If you've configured a trigger event to capture the recording around a specific scenario, then you will want to leave this box unchecked so you don't have unhelpful scope files. The default of 100 milliseconds for the request cycle should work for most situations. The number of log files is important for how many recordings you want uploaded automatically. If you select unlimited, the scope files will keep being uploaded until you stop the data logger. If you uncheck unlimited, you will want to specify how many uploads you want before it automatically stops. Depending on your trigger method, it's possible for non-relevant things to trigger the recording and fill up the set number of log files and not capture the information you need. So you may want to set a higher number to account for recordings that may not be useful, or configure a more precise scope trigger so that way you're not having to sort through unhelpful data. And the complete data upload refers to when the parameter file should be uploaded. I haven't found any difference between these choices because the parameter file will always be uploaded alongside of the scope file, so what you choose here isn't critical. Over on the right side, you will need to click this folder icon to set where the parameter and scope files should be stored. I recommend to put them in a dedicated folder so that it's easier to keep them together since there could be a lot of files uploaded. Also, the file name can get long, so I recommend to create the folder not too far nested in your file path, otherwise Windows can present a destination path too long error. In this example, I created a folder at the root directory of the C hard drive, so that way the file path isn't nested in any user folders. Here is where you can give a prefix name to the files that will upload. Then you can select if you want the date, time, or a sequential number to be included in the file name. You can see the preview of what the file path and name would look like below. One of the most critical checkboxes is this Create SCX file. You must select this if you want scope files uploaded, otherwise the only thing uploaded will be parameter files. This is the file extension of the scope recordings, so you must not forget to check this box. After you checked that the settings are how you want them, then you can click on the Next button. Now you're at the control screen, and this is what needs to remain running without the computer shutting down to upload the recordings and restart the scope. When you're ready, you can click this Start Monitoring button to start the logger. Once the logger is running, the progress bar moves back and forth and the lights indicate different states of the scope tool. Once the scope has been triggered, the logger will automatically upload the data and store the recording in the file location you set, and then restart the recording after the fault has been reset. If you set a limit to the number of scope recordings uploaded, when that limit has been reached, the logger will automatically stop and then show this message that the max has been reached and that it's finished. If you need to restart, then you can click the Start Monitoring button again, and it will restart the logger and keep uploading files until the maximum number of uploads is reached. I do recommend you check the scope files you have so far because it is very possible you will need to adjust the scope recorder settings and start over to capture the data you need. If you go to where you stored the scope files, this is what you'll see. If you didn't forget to check the SCX file extension checkbox, then you will have the scope files. And for each scope file upload, there is also a parameter file. The parameter file can be helpful to run a comparison using the MOVIDRIVE software to determine if any parameters changed between the recordings. Or you can open the parameter file and view the fault history, which can give clues to what caused the scope to trigger. If you have a timestamp record of when the problem situation occurred, then you can look through your files to find a scope file around that time frame and check the recording for any clues to the root cause. If you don't see a file around the time frame that the problem occurred, then your trigger may not be configured to catch the issue. So you will want to try some other trigger methods and wait for the problem to occur again. If you're watching this in the United States and need technical support for your application, we have assembly centers across the US that have engineering departments to assist you. Our engineering departments can assist you over the phone, email, or on-site at your location. For the western half of the US, our Hayward, California office would be your contact. If you're in the Midwest, we have an office in Troy, Ohio that supports these states. If you're in the Northeast, we have an office in Bridgeport, New Jersey. In the Southwest, our office is in DeSoto, Texas. And in the Southeast, we have an office in Lyman, South Carolina. These are the main phone numbers at these offices, and when you call in, you can ask to speak with regional engineering if you need electrical or mechanical technical support. If you're located outside of the United States, we also have technical support offices across the world. To find your nearest SEW office, you will need to navigate to our corporate website, which is www.sew-eurodrive.de. At the time of this video recording, this is the way the web page is designed, and to get to the interactive map that shows the locations across the world, you will click on the Company tab on the right of the web page, and in the pop-down menu, there is a link to click on Worldwide Locations. This will open an interactive map, and you can zoom into your region and find the nearest SEW office and contact them for personalized support of your application and devices. Okay, we have reached the end of our 7th and last training session. What we've presented so far in this online training series is the same material and exercises that we would cover if we were teaching this topic in person. During this troubleshooting session, I did mention for you to go back and watch several of the previous videos that we have covered, which offer more in-depth instruction, such as using the Scope tool and how to troubleshoot brakes, motors, and encoder connections. So in the description below, I have placed links to those videos so that you can find them easier. I hope that you have found these videos helpful. If you have further questions or if you need support for your application, please contact your nearest SEW EuroDrive office. Thank you for your attention. Take care and have a good day.